Hey, hi everyone. Good morning, and let's continue the discussion from where we stopped yesterday. So, just to do a quick revision, hypothesis testing. It's basically the testing of assumptions, and whenever we have a business problem, we need to first make assumptions and then prove the conditions. And based on the evidence that we get, we go by one of the assumptions that we had made. And always we start with the default condition as the good condition. So we are assuming that whatever we're currently doing is the good condition, which is called as null hypothesis. And we are basically trying to prove that if I take action, if I do something alternative to this, then what is going to happen? It's called as alternate hypothesis. So here null hypothesis basically is your current condition. We can also say whatever your default condition is, that can also be taken as null hypothesis. We also say that this is a condition where you'll not take a new action. You'll continue doing whatever you are currently doing. Alternative hypothesis is do something different from your regular stuff. So we will call it as take action scenario. So your status quo would be null hypothesis. And opposing that, we get alternate hypothesis. So this is hypothesis testing that we discussed. And we have also seen the conditions that might arise. So here we are assuming 4 cases because it is a 2-case scenario, null hypothesis, alternative hypothesis. So if null hypothesis is true, then we should go with it. So we say, I don't have evidence to reject it. So I fail to reject null hypothesis. And this would be your current condition, which is called as confidence. We call it as 1 minus alpha. And if null hypothesis is true, but we have some evidence, which may be false evidence, and we are rejecting null hypothesis, then this is called as type 1 error, which is represented as alpha. Now assume if alternative hypothesis is true, but we don't have enough evidence to reject the default condition so that we can take alternate hypothesis condition, then this is called as a wrong decision, and it is known as type 2 error, which is beta, represented as beta. And if I am rejecting the null hypothesis to take the correct alternate hypothesis, then this is again the right decision. And this is the power that this test gives us to take an action which is different from your regular stuff. So this is represented as 1 minus beta. We generally call it as power of the test. So this is hypothesis basically that we have discussed yesterday. And let us proceed further. Let us proceed further to understand what various steps that we will do, or what various tests we can do when we are basically looking at these business problems, looking at the data. Now, when we are doing null hypothesis, always remember we need to first understand the business problem. Now, this is the process that we have to follow. By looking into the business conditions, business statements, right, talking to your clients, we understand the business problem. We define objectives and constraints. And from these objectives, constraints, and from the understanding, we have to frame the statements. Assumptions have to be framed. Right? Start with hypothesis. But when you are framing the statements, always remember, we frame the statements for population parameters. We are generalizing the problem. Right? But to prove this, we do inferential statistics. That means when we collect the data, we only get sample data. And on the sample data, we get statistics. And using the statistics, we have to basically conclude on the statements that we are making, the assumptions that we are making. So statistics will vary, right? So we do inferential statistics to estimate population values. Population parameters have to be estimated. Inferential statistics. And based on the population parameters that we are getting, we would either reject or fail to reject the default assumption. We take that conditions. Now, when we are finding the population parameters, we assume that the condition is normally distributed. Of course, those are called as parametric test cases. And we see whether the result that we are getting is falling on the accepted region. Accepted region is nothing but 1 minus alpha, confidence. And this becomes your rejected region. So if it falls here, then it is rejected region. We can say this is alpha by 2. This is alpha by 2. So what we are ultimately doing is, we are assuming that whatever we are doing is good. But because there is a question that basically prompts us to think an alternative idea as well, about alternative option as well. Before we take that alternative option, we cross-verify, we evaluate. As part of that evaluation, we basically take a pilot launch. We do a pilot launch. We take a sample data, right? We do conduct experiments and see what is the result if I do an alternative action. Right? So this inferential statistics, you can assume that I'm doing a small experiment on the alternate idea that we have, or alternate option that we have. And we get the results, and these results are being generalized. Population parameters have to be estimated for them. And then we see that whether the result that we are getting will fall in the accepted region or rejected region. If it is falling in the accepted region, then no problem. You can continue taking the alternative option because it is better. You're feeling that alternate option is better than what you're currently doing. So we go ahead with alternate option. But if the result is falling in the reject portion, then there is no point in taking the alternate option, right? Rather, better continue what you are doing. That is the business level of interpretation of hypothesis testing. And here, to interpret that, we look at the probability value, p-value. This p-value basically is the chance of going wrong if we go by alternate hypothesis. If I take alternative hypothesis, what is the chance of going wrong? From the predefined parameter. Now, if this p-value says it's greater than alpha, where alpha is the significance level, which basically says this is the standard, or this is the maximum chance that we have to go wrong, which is industrially accepted. So we are comparing these two, and we say if your p-value is more than what is accepted, that basically means what? If you're conducting the experiment here, you have more chance of going wrong, so better go with null hypothesis only. Don't take that option, right? And then we also have another option where we say the p-value that we are getting is less than alpha. So 5% is accepted, right? And the chance that you are going wrong is less than 5%. So there is no risk, right? In that case, you can go ahead with alternative hypothesis. This is what we have learned yesterday. And there are flowcharts that we have to look at. The flowcharts basically talk about what is that value that we are evaluating. If that value is continuous, then there are certain conditions that we need to follow. And we have looking at this particular flowchart yesterday. We will try to cover a few of these cases today. And if it is discrete, don't worry, it is very easy. We just check the proportions of the values and we take a decision. So this is what we will continue doing today. The fabric data is what we have done yesterday. We took a sample of data. We had measured the standard. We have considered the standard as 150 meters. Then the average variance, that is standard deviation. On an average, the deviation in the length of the mean was given as 4 meters. And then we have estimated a population mean for the current sample data at a significance level of 5%. And then we concluded that the current mean was greater than the 150 meters, that is standard. So that means the machine was cutting the length at a higher value. More length was given. So we had to stop the production and then check the machine and perform the maintenance task to make sure that it doesn't cut away the additional cloth or additional fabric. So let us now try and look into another example. We are doing a non-parametric test case. We're working with a non-parametric test case. Okay, what does that actually mean? We'll see that. Fuel additive. Fuel additive basically means in our regular fuels, we have some additional lead content or additional components are mixed to give extra mileage or extra performance, right? So effect of that additive which is getting mixed into the fuel is being studied here. So randomly, there were 20 vehicles which were taken. Out of these 3 vehicles, 10 vehicles were chosen again randomly, and the mileage of these 10 vehicles and 10 vehicles separately were recorded. So first 10 vehicles, the regular fuel was added and the mileage was recorded. In the next 10 vehicles, additive fuel was added. We wanted to test that additive, right? Effect of that additive. So that fuel was added and the mileage was recorded. So I have 10 vehicles with regular fuel, 10 vehicles with this new fuel which needs to be verified. Right? And mileages were recorded. We want to find out if I mix the additive into the fuel, is it affecting my mileage or not? Is it increasing my mileage or not? This is what we have to do. Now, in order to do that, first we need to frame the statements, isn't it? So the business objectives, that we have identified the business problem we have to identify here is, will the mileage get improved if I add this additive here? So my null hypothesis and alternative hypothesis, we need to frame the statements for generic cases, for any vehicles, right? Generalizing. So my null hypothesis and alternative hypothesis, when I want to frame the statements, I would say, because I have two samples here, sample 1, sample 2. Sample 1 basically says the regular fuel mileage. Sample 2 basically says the additive fuel. Right? And mileages are recorded 1, 2, 3, 4, so on and so forth, 10. Here also I have 1, 2, 3, so on and so forth, 10 vehicles. Alright? So I'm saying mileage, representative value of this mileage will always be mu. Average mileage of regular fuel vehicles is equal to average mileage of additive fuel. If this is the case, should I take action? What is the default action here? The default action says use your regular fuel. You don't want to add anything extra, right? So if this is the case, you can clearly see that there is no effect of the additive fuel on the mileage. So in that case, I go with regular fuel, right? No action. This is equal to, and I can say miles per gallon of regular fuel is not equal to miles per gallon of mileage of additive fuel. So here, yes, you need to take action. That action basically is saying, try and identify which is more. Is additive fuel more or regular fuel more? Isn't it? If my additive fuel is more, so this is, let's say, case 1. Always in hypothesis, remember, we first check for equality. Because if it is equal, even then you can take a decision directly, right? You don't need to go to the next level. But anyways, yeah. Null hypothesis and alternative hypothesis, I'll be rewriting here. If I find, by chance, if I get alternative hypothesis in case 2, then I would say average mileage of regular fuel. When would I not take action? When the mileage of the regular fuel vehicles is greater than the mileage of the vehicles with additive fuel. So here again I go with regular fuel. But if the mileage of additive fuels is greater than the regular fuel vehicles, then yes, we can say that the additive fuel is improving the mileage. So in this case, I would conclude saying that additive fuel should be taken. All right. Wonderful. So I will take up your questions again in every half an hour break. So let me make sure that you're, if you have any questions, make sure that you're drafting them. You can message them in the chat window. And yeah, I'll get back to your questions in the break. All right, so we framed the statements here. Now we need to look into the data, right? We are collecting the mileages. Remember, we are trying to evaluate the mileage. So I'm saying miles per gallon. right? This value is continuous, right? So if it is continuous, I would have to go with the first thing is normality test. So the first thing that I would do is verify whether the data is normally distributed or not. Yeah. So this flow chart basically tells us that Y is continuous, fine, but the number of groups that we have, X, which is a factor, right, is 2. So this is the branch that I have to follow, the center branch, the middle branch, right? And it says the first step that we need to do is normality check. Always remember, whenever the data is continuous, we have to verify whether it is normally distributed or not. Okay, so let us do that. So let me erase this and put it on. Let me erase all this. All right. So I'm going to load the data set here. So I have 10 rows, 2 columns. 10 rows, 2 columns. The first column says without additive. This is your regular field. And the second column says with additive. And this is additive field. So let us see this. And the first thing we need to do normality test. And when we are doing normality test, we would check whether the data is normal or not, right? So again, verification. We write null hypothesis and alternate hypothesis. We say whether the data is normal or not. And the default assumption for normality test is data are normal. And here we say data are not normal. So we'll proceed with this. And we do AD test, which is Anderson-Darling test. So I'm loading the normality test library, and I'll simply do AD.test of the first sample. And this gives us the p-value. The p-value here is greater than 0.05. 0.7127 is greater than 0.6. So p high, null fly, which basically says fail to reject null hypothesis. Right? We are failing to reject null hypothesis. That means we go with null hypothesis itself, which says data are null. Now, you might want to check this, right? Let us check this using QQ norm. So QQ norm of additive dollar without additive, right? So this is the first column. And if I say QQ line here, we can see that the data basically is falling on the straight line. Majority of the data is falling on the straight line. So this is normally distributed. Now let us also check for the second sample, which is additive field. And what does this additive field say? The Anderson-Darling test results in a p-value which is less than 0.05. If it is less than 0.05, then the slang, the statement that we have is p low, this is lower than this, p low, null, go. P low, null, go. right? We can also cross-check this again using QQ norm, additive, dollar with additive. And you can see here the diagram. So very few data points, maybe 1 or 2 data points are falling on the straight line, but other data points are not on the straight line. So this clearly tells us that the data is not normal. So when we have this kind of cases, the first solution that we try and apply is to do transformations. Try and apply transformations on this particular data to convert this into normally distributed data. But whatever the transformation that you have worked on this non-normal data, it should work, right, on this normal data as well. The same transformation should work, right? And this also should remain normal. Here also it should remain normal. Okay, that is basically what we need to do here, which is a little tricky, especially when we have a large number of samples, right? And here, assume that we have tried few transformation techniques and it didn't work. The data did not become normal. So when the data does not become normal, we try doing non-parametric test cases. Non-parametric test cases. Yeah, that non-parametric test cases basically are saying that do not use mean because the data is not normal. So in the non-normal test cases, in this test case, we call it as Mann-Whitney test case. We follow medians. Or another way, we compare the median mileage of the groups. We do not compare the means. We do not compare the means. We compare the medians. Okay. So let us do this Mann-Whitney test case. Remember the statements that we have done. The first statement would be equal to, not equal to. Case 1. And we say median of regular fuel is equal to median of additive fuel. And median of regular fuel is not equal to the median of mileages of additive. Median, we are just replacing mean with median. And this is a two-sided test, not equal to. So you're basically saying whether the value falls here in the accepted region or not falls here. Not false means it could be here or here, right? So we are saying it is a two-sided test. And Wilcox test, if you do question mark of Wilcox, it says Wilcoxon rank sum unsigned rank test. Performs 1 and 2 sample Wilcoxon tests on vectors of data. The later is also known as Mann-Whitney test. Signed rank test is also known as Mann-Whitney test. So I'm saying sample 1, which is without additive, with additive. I'm not taking mean, I'm taking median, and this basically mu means whether the averages are equal to 0 or not. That basically means the null hypothesis says that median of regular fuel minus median of additive fuel is equal to 0, which basically means these medians are equal, right? So that is written here. Median is equals to 0. And then we have two-sided test, not equal to, and the confidence level is 95%. Exact means true, which basically says calculate the exact values, and I execute this. So what is the p-value that we are getting? The p-value here says greater than 0.05. P greater than 0.05 basically means P high, null, flood. That means we fail to reject null hypothesis. Fail to reject null hypothesis, which basically says that the mileage is not getting affected. The conclusion here we can say that the mileage additive is not affecting the mileage of the basically mileage of the vehicles. So this is how we conclude by applying medians when the data is not normal. Okay, that's the first case here. This one, Mann-Whitney test. This is called as Mann-Whitney test. So let us move on. We'll now look into another case. So a financial analyst at a financial institute wants to evaluate a recent credit card promotion. And after this credit card promotion, 500 cardholders were randomly selected. Half received an ad promoting full waiver of interest rate, right, on purchases made over the next 3 months, and half received standard Christmas advertisement. Did the ad promoting full waiver interest rate increased the purchases or not? Increased purchases or not? So let's say a financial institute which gives credit card, let's say bank is basically evaluating an offer. So they want to launch an offer. Right? They cannot blindly launch it. So what they are doing is, a financial analyst, a manager, for example, he randomly chooses customers after releasing the offer. So they said that, okay, let me do a trial launch, and he launched this to the customers. And from these customers, they have randomly selected 500, or from all the customers, and then they split this in such a way that 250 customers were given the regular offer, 250 customers were given the new offer. So the new offer, recent credit card promotion, right, is full waiver of interest rate. And the remaining half received the standard Christmas advertisement. Christmas advertisement. And we want to now check whether the purchases using these offers, right, are more or not. For credit card, right, if you're talking about a credit card promotion, basically it should enhance customers to use the credit card more often, right? So did this offer, 2 offers I have, right? Which offer is encouraging customers to purchase more? That is what we need to check here. Now the recent credit card option offer is full interest rate waiver offer, and the bank wants to launch it only if it makes sense, right? Only if it makes difference or only brings profits, right? So if customers are using the card more, if this offer is given, then it makes sense to launch it. Otherwise, there's no point in marketing and right, doing advertising and launching all those that offer basically. That's not required, right? So this is basically our business problem. I'll write it here. Should the new offer be launched or not? This is the question, the business problem that we need to take. And the null hypothesis and the alternative hypothesis is We would launch the offer only when it is enhancing the purchasers. So you see, average purchases using full waiver of interest rate, if it is equal to the average purchases of standard Christmas promotional offer, would it actually make sense to launch this new offer? Not right. You can see that there is no difference. So why you want to invest into your new offer? Put those efforts somewhere else, or put those efforts to marketing the existing offer further better. So I said no action. I don't want to launch the new offer. Right? But if the purchases are not equal, that's when I want to basically cross-check which offer is better so that I can take an appropriate action, right? So take action here. Just like the manuality test that we have seen, the mileage cases, here also we do case 2. And in the case 2, the null hypothesis says average purchases of full interest rate waiver offer is greater than average purchases of, or average purchase, right, of customers using standard Christmas offer. Oh, sorry, my bad. It should be less than. So this should be less than. That means the new offer is not encouraging customers to purchase. So in this case, why you want to launch? It is not affecting the purchasers, right? So don't do that. Do not launch the offer. But when you have greater than, the purchases are greater, then you are going to take action. Here, take action. So this is basically how we frame the statements, and let us now solve this problem. Okay. Of course, next we'll do the PT test. Let me do this test here first. So we load the data set. I have 250 rows. Each column basically has standard the purchases made by the offers, interest rate waiver offers, and standard promotion offers. But one thing you need to remember with the programming languages R and Python, of course, both these are languages, right? Any programming language that we talk about, when you are using variables, these variables have certain standards. First standard, it cannot start with number. Cannot be started with number. The second point, no special characters, including spaces. You cannot have special characters, only dot or underscore or accepted. Okay, these are the two special characters which are allowed. So here I have the open brackets, the brackets, open and close brackets, dollar symbol, and spaces as well. Yeah, it also has spaces. You can see that. So we are renaming them into these names so that there are no spaces anymore. Right? So let me change this. You just say column names of the data set, and you're giving the column names. And now if you view the promotions, you can see the names of the columns are appropriately given. So we attach the data, and then I'm doing normality test. Now all this while we were doing Anderson-Darling test. Now in this particular scenario, we are doing Shapiro-Wilk test. This is another test which is defined by another scientist. Shapiro-Wilk test basically is also verifying normality. Here also we check p-value, and Remember, for normality test, we are always checking whether whether the data are normal or not normal. And the default assumption is that data are normal, right? So, null hypothesis, data are normal. Alternate hypothesis, data are not normal. And we got p-value which is greater than 0.05. So, we say p high null fly. That means it follows normal distribution. Null hypothesis is what we consider. This is for the first column. Similarly, we are doing it for the second column, standard promotion offer. So we execute this now, and we are getting a p-value which is again greater than 0.05. So p high null fly. Again, we say it follows normal distribution. So both the data points, both the populations that we have are following normal distribution, right? Now, if it is following normal distribution, let's see. We first verify that we have two samples, right? Y that we are looking, which is purchases, is continuous. And X, which is a factor, we have two samples, full waiver of interest rate and standard Christmas offer. Then we verified normality test and we found that the data are normal. The data that we have got are normal, both the samples. Next immediate question, look at this. External conditions are same. So we need to see the data that we are considering in both these groups, right? And we have to see whether the factors which are influencing the value, which is purchases, is that value getting affected by any external factors. For example, here, the analyst has randomly taken 500 customers and then randomly split them into 250 customers and 250 customers. Now, do we know who are these customers? We don't know. What are their bank balance? Do we know that? We don't know. What is their gender? Not sure. What is their location? Not sure. Right? Location, basically the country. Right? What is their card limit, for example? You're giving credit card offer, but do we know their card limit? We don't know. So there are a lot of factors like this which are influencing the purchasing capability of the individuals who are there in this sample and in this sample. Because your sample data itself is different, so the external conditions are not same. We will see. If the conditions are same, what should we do? Right? It's called as paid t-test. It's very easy. We'll do this after the example. So here, the external conditions are not same. Now, if the external conditions are not same, then we verify the variance test. We'll understand why we need to look at variances. Probably the later part of the sessions we'll understand that as well. So we are looking at whether the spread of the data between the two samples are similar. On an average, you have a mean, but is the spread from that mean, is it similar or not? Right? So that's what we are basically verifying. And the variance test, null hypothesis and alternative hypothesis basically say equal or not equal. Variances are equal or the variances are not equal. So let us go to the code. So variance test, you simply do var.test. That's the variance test. And you just sample 1 and sample 2. Execute it. And we get the p-value. The p-value is again greater than 0.05. It is greater than 0.05. So we again say p high, null flat. P-value is higher than alpha, right, which is the industrial standard. So we say p high, null flat, passed with flying colors. This basically implies we fail to reject the null hypothesis. That basically says that go with null hypothesis. Your null hypothesis condition is correct. It says variances are equal. Right? Variances are equal. Now variances are equal, hence we look at the actual business problems, the case studies that we have written, right? The hypothesis statements that we have written. Mean of full waiver of interest rate is equals to mean of the standard Christmas offer. And we said not equal. This is null hypothesis. This is alternate hypothesis. Yeah, null hypothesis and alternate hypothesis. Right. So this is two-sided, friends, again. Okay, so let us execute this. The test that we are using two sample t-test. It says t.test, right? And by default, the variances are treated as equal. If you put false here, that means we are assuming that the variances are not equal. So it's that simple. Performing hypothesis testing is that simple. It's changing the parameter. So p-value that we are getting here is 0.024. Now this p-value is less than 0.05, right? So we say p low, null, go. So null hypothesis, alternate hypothesis. Null go means we are rejecting this. Go away. So we say reject null hypothesis. What does our alternate hypothesis say in this case? It says that the means are not equal. So if it is not equal, if the means are not equal for the samples, then which mean is greater? We need to identify that so that we can consider one of the decision, right? We can consider and take a appropriate decision. So we say average of full waiver of interest rate offer is less than standard Christmas offer average. This is where we take no action. No action doesn't mean you do not give any offer. You're basically saying I don't give the new offer. And alternative hypothesis says full interest rate waiver offer average purchases is greater than standard Christmas offer. So here you are doing the action. It says launch the new offer, which is full interest rate waiver offer. So you basically will be able to take an appropriate decision to your business problems. So only thing that we alter here is the alternate hypothesis here that you are drawing, right? It's just basically saying greater than. So you are putting that. Sample 1 is greater than sample 2. That's it. You're done. And what is the p-value that we are getting here? The p-value says 0.012, which is again less than 0.05. Industrial standard significance level alpha, 5% chance of going wrong. And we see that the chance of it going wrong is less than that. That means there is no risk if you take action. So we say P low, now go. Reject null hypothesis, isn't it? So reject null hypothesis, we basically go with the alternative hypothesis here. And alternative hypothesis says, go ahead and launch the new. Go ahead and launch the new offer. So this is how we conclude. The interest rate waiver offer is better promotion than standard promotion offer. Right. So this is basically how we deal with the cases where the data satisfies certain conditions. Normality, yes, if the data was satisfying. External conditions, they were not same. So we came here, then we verified the variance test. And based on these results, we followed two sample t-tests for equal variances. Right, two sample t-tests for equal variances is what we did. Now let me take up your questions. Let me see if you have any questions here. Okay. I don't have any questions here. Let me see if I have any questions. Okay, I see a question. Testing for hypothesis is part in EDA level in ML. It's an inferential statistics stage where you perform hypothesis testing. You may use it for doing some kind of estimations if that is required for doing some kind of descriptive analytics. But I cannot say it is purely for EDA. It is also used for doing some predictions. Ultimately, it is doing predictions if you observe here. It is estimating a value, and then based on that value, you are taking the decisions, right? Right. So you cannot purely call it as an EDA, but yes, it is a mix of both descriptive and predictive analytics. We generally call it as inferential statistics. Yeah, so I see only one question. All right. Let us move on and discuss about the next topic. Okay. So we are going to see a case of sleep drug test. Sleep enhancing drug is being examined. So an experiment was conducted to verify which of the two drugs, enhances the sleep time better. So the experiment was conducted in a way that they randomly selected 10 volunteers, you can say 10 students or volunteers, and their extra sleep time was recorded when they were given drug A and drug B, right? And we need to find out any evidence is there to prove or to find out which of these drugs is improving the sleeping patterns in the students. So my business problem is to identify which drug is better. You can basically talk about the same thing with respect to your COVID-19 case. So multiple medicines are tested. Which medicine is better is what we need to understand. So let us see the business problem. The business problem says, which drug is better? Which drug is better in enhancing sleep? It should make sure that the person is sleeping a little more. Right? That's the idea. And what we have done here is we have taken 10 students or 10 volunteers. And for these 10 volunteers, drug A was given. And their extra sleep was captured. First, second, third, fourth, so on and so forth. For the 10 volunteers, what was the additional time that they slept? Similarly, for the same set of 10 volunteers, drug B was given and then the extra sleep was captured. This is the experiment we have done. Now we need to prove, right, on an average whether this extra sleep that the students had or the volunteers had is more or this is more. Again, we have only sample, so we have to estimate a population value, population parameter, and then compute. So let us try solving this problem. We'll come here. There's a package called stats. I require that. I load it, and I have a data set called sleep. This is the sleep data. Extra basically means the extra sleep hours. Group basically is the drug ID. We have group 1 and group 2. In total, I have 20 records. You can see the first 10 records say group ID 1. The second 10 records say group ID 2. And you can also see the ID, which basically is for the individual volunteer. Here 1 to 10 is there, and the same 1 to 10 is repeated here. Okay? So first things first, what is that we are evaluating? What is the value that we are evaluating here? We are evaluating extra sleep time, additional sleep time. So time basically is continuous. And we had two groups, two drugs, right? Drug A, drug B. Which is better is something that we need to verify. So first things first, we need to check normality test. Let us do that. This is basically to understand the data better. So table of the group would basically give us 10 and 10. Attach of sleep, I'm doing this. So here I'm first checking whether the data that I have is normally distributed or not. I'm taking the entire data set, not splitting it. I'm taking the entire data set and checking. You might want to split it into two parts where you say drug ID is equals to group ID is equals to 1. For that, what is the normality? What is the data, whether it is normal or not? And then you also split that with drug ID 2, group ID 2, right? And then verify it separately. But here, yeah, we are testing it as a single group. And we found that the complete data that I'm taking is normally distributed, right? You can also basically see, if you want to do this, I'll say rows and columns. I'm taking the extra column, and in this extra column, I'm basically taking the first 10 records. So I'll say 10. Oh, sorry, my bad. Let me put it like this. Sleep, the first column, and I'll say combination of one column. So the first column and 10 rows. This is your first column extra and 10 rows. Easy way to check. Why is this? One second. It's data frame. Sleep, one column. Number factor ID. All right. So I'm taking basically the wrong way. My bad. Yeah. So first 10 rows, first column. P-value is greater than 0.05. Right? Similarly, you might want to do for this second set of 10 values as well. So you say from 11 till 20. And this is also greater than 0.05. Right? So the complete data set that we are taking, which is getting segregated into two groups, and we are verifying whether the data is normal or not. And we found that the data is normal. Right? The data is normal. Hence, we can conclude that the data is normally distributed, and we move on to this next condition. This is important for us to understand. Are the external conditions same here? So we are taking 10 students, right, or 10 volunteers, and then we tested them with drug A, and we recorded the sleep time. Now the same set of 10 volunteers were tested with drug B. Underlying my sample is not changing, right? If my underlying data is not changing or the sample is not changing, then I can assume that the conditions are same. Right? These people are made sure that they slept at the same time because their underlying personalities are same. If other external conditions are assumed to be same, then there is, right? We can safely conclude. Basically, there is a proper evidence, or we can safely assume that the external conditions are same just because your sample data, the volunteers that we are taking, are same. But if you would have tried with different set of people, 10 students drug A, 10 students drug B, then it becomes different conditions, right? Because you're testing the drug which goes inside the body, right? So the body is same, then other conditions can be made same. So we assume that the external conditions are same here. If the external conditions are same, then we do paid t-test. Okay. So the paid t-test basically looks at, or the test is performed when the same set of data is being considered to verify the effect of a specific parameter. Right? So here we are verifying drug effect on the same set of data, two drugs. So here we are doing two-sided test again. Case 1. We say the sleep time for the two drugs is same. Yeah. And we basically say not equal to. Alternative hypothesis is not equal to. And we do this t-test. The same t-test can be used for applying paid test as well, and you basically have to pass this particular caption or the parameter which says paid is equals to true. You can do a question mark. P dot test performs 1-2 sample t-test on vectors of data. Okay, paid is equals to false is the default. A logical value indicating whether you want a paid t-test or not. So I'm saying yes, I want a paid t-test here. So let us apply this. And the p value that we are getting is 0.002. The p value is 0.002. And this is very, very less than 0.05. So p now go fail to reject null hypothesis. Reject null hypothesis. That means to take all the hypothesis which says true difference of mean is not equal to 0. Cannot. So we move on and come to one-sided test. Drug 1 is less than drug 2 and drug 2 sleeping patterns. Null hypothesis and alternative hypothesis. We frame the statements here. And let us try and do the same test. Same test. Except now the alternative is greater than. By default, it is always two-sided. But the alternative is greater than. Sample 1 is greater than sample 2. Execute it. And what is the p-value that we are getting here? 0.9986. 0.9986. This is greater than 0.05. P high, null, fly. P high, null, fly. That basically means drug 1 sleeping patterns are greater than drug 2. P high, null, fly. Null pass, basically we are saying we fail to reject null hypothesis. That means we are going with null hypothesis, which says, oh, sorry, my bad. Drug 2 is greater. Drug 1 is less. My bad. So this is how we frame the statements. So we have verified this evidence that the mean difference, true mean difference is greater than 0. Right? When we do the subtraction, we get the negative value, right? It's not greater than 0. We get a negative value. Because drug 1 is smaller, drug 2 is greater. So when you do subtraction, you get negative value. That is what is shown here. Right? So at 5% significance level or 95% confidence level, we are saying that drug 2 is better. Drug 2 is enhancing the sleeping patterns. This is your paid t-test. Paid t-test. This one. Okay, I think I have a question here. Let me try and answer that. When do we use Shapiro and AD for normality? These are different test stuffers. You can try out any test, your wish. AD test or Shapiro test, or there is something called as cosmonograph, Smirnov test. Different tests are there. Okay, but most often, frequently used test cases are AD test and Shapiro test. You can try out. There is no restriction. All right. Next. A marketing organization outsources their back office operations to 3 different suppliers. The contracts are up for renewal, and the CMO wants to determine whether they should renew contracts with all suppliers or any specific supplier. CMO wants to renew the contract of supplier with the least transaction time. CMO will renew all contracts if the performance of suppliers is similar. 3 suppliers and see which supplier is working better. Least transaction time, they should complete the task in the least number of time, right? Among the 3. And CMO, Chief Marketing Officer, would renew the contracts only for those suppliers who have better performance, right? So the business problem is which supplier's contract should be renewed. Contract renewal, right? Which supplier contract should be renewed? That's the business problem. Okay, I'm just writing the keywords there. I'm not writing the entire statement. Now, null hypothesis, alternative hypothesis. These contract renewals are being performed or being decided based on the transaction time. So transaction time would be your output because that is the value which is being used to evaluate. Transaction time. Right? And we have three groups. So my null hypothesis says that, always remember equal to, right? So I say transaction time of supplier A or supplier 1 is basically equal to transaction time of supplier B, and this is equal to supplier C. A not equal to B not equal to transaction time of C. This is what we can basically frame the statement as. But there is a challenge with this particular statement. We cannot write this way because in the alternative hypothesis, in null hypothesis, it is fine. But in alternative hypothesis, you may get this case. They're not verifying that. And if I have a scenario where I have this is also opposing your null hypothesis. Anything which is not null hypothesis is alternative hypothesis, right? And it is not null hypothesis. So we cannot write the statements like this. Whenever we have greater than 2 samples, when you are doing this comparative analysis, we say all the sample means are equal. At least one sample mean is different or is not equal. Do this or do this, you will get the same. Mean is different or mean is not equal. Either statement, both are same. So this is how we frame the statements for the Anova test. When you have greater than 2 samples. So if I go to that flow chart, if I come here, the output variable is the transaction time. Of course, it is continuous, so we follow this flow chart itself. And X is a factor, and here I have 3 suppliers: supplier 1, supplier 2, supplier 3, or you can say ABC. Because it is greater than 2 populations, I come to this branch. We come to this particular branch. And just like any other test case, if your data is continuous, we need to verify for normality. And the normality test conditions would remain same. We say data are normal, that's the default assumption, and data are not normal. We come here. And let's load the data set and see the data. I'm viewing my data. So I have 3 suppliers: supplier A, supplier B, supplier C, and their transaction types. So we need to basically take the average transaction times and compare them, right? And just like any other test we have done till now, we look at first normality test. Either you do Anderson-Darling test or you do Shapiro test, both are fine. Here the p-value says it is greater than 0.05. Supplier B, this is also greater than 0.05. and suppliers. So the suppliers here, the data that we have, are normally distributed because all the p-values are greater than 0.05. So p high, null, null. But data are not, data are normal. So the first test successful. Then we go to the next test, variance test. On the variance test, we are checking whether the variances are equal or not equal. You can say var.prest f test to compare two variances. And we are basically checking whether the variances are equal or p-value, the variances between A and B greater than 0.05. So the variances are equal. 0.6347, again p-value is greater than 0.0705. B and C, this is also variances are equal. Finally, C and A. And here also we get the variances equal. So we are basically checking the variances being equal between the pairs AB, BC and C. Yeah. Now, the case here that we need to look at is, what if any of this one supplier being not normal, or what if any one of these variance tests that we are getting is not normal? That means the p-value will, if it is less than, then what should we do? We have already discussed this. People who have joined the session a little late, let me repeat for them. I am looking at checking whether the data is normally distributed or not, and I have three suppliers. Let's say this is normally distributed. This is not normal, assume, not normal, and this is normally distributed. So now I need to make this as normal. That basically means the p-value here it is greater than 0.05, here it is less than 0.05, and here it is greater than 0.05. Right? So for non-normal data, to make them normal first, we apply transformations. Now let's say by doing log transformation, become normal. Remember, we are comparing the average transaction time. So if it is in, let's say, seconds or minutes, whatever it is, right? Seconds or minutes. Here I am taking, let's say, minutes. But here I am taking log of minutes. And here I am taking again minutes. Do you think the scale would be same for the three groups? No, right? I applied log transformation here. So the scale definitely gets hit there. So I would not be able to compare them, isn't it? So what we need to do basically is apply the same transformation to y1. So you say log of y1, log of y2, and log of y3 also. And then verify whether this is normally distributed. Yes, this became normally distributed when I applied log. And what about this? Now we consider the transformation technique which keeps all the three normally distributed. So finding such a transformation technique would be a time-consuming task. But yes, that's what we have to try and do. Now, if I try a lot of transformation techniques and nothing works, then we have non-parametric test cases, right? Non-normal test cases happen. In this case, we call it as Moore's median test. Probably you have to explore a little more, Try and read about it. And remember, in all the non-parametric test cases, we use variance for comparison. Then we come to variance test. And we verified that all the variances are equal. Hence, we are going with Anova test. We'll also see ANOM test. After this, I'll explain ANOM as well. So here we considered, or we concluded that Anova test should be performed. Now, in order to perform Anova, we need to check, or in order to perform Anova, we need to see whether the data that we are passing is in a single column or not. If you look at this, the data is in 3 different columns. Supplier A, supplier B, supplier C. So we need to stack that data, combine them. So a simple command stack would basically bring up the entire data into a single column like this. Supplier A, index, supplier A comes first, the first column, right? And then comes supplier B from 120, supplier B, and then the third column, supplier C. Okay, so we are stacking them up. And then let me attach the stacked data, wherein you have 2 columns called indexes and values. These are the 2 columns you can provide, values and indexes. And the Anova test that we are performing, we do AOV test. AOV basically is Anova. Do a question mark and just fit an analysis of variance model. So we are trying to fit that model. But before this, remember the hypothesis that we have framed? All the sample means for the transaction times are equal for the 3 samples. And alternative hypothesis says at least 1 sample is not equal. Perform that. And we are doing summary of the results that we are getting, which basically shows the p-value. And the p-value that we are getting here is 0.104. Right? So we're basically saying whether the mean samples are equal or not equal. Null hypothesis is equal, and here the p-value is greater than 0.05. So p high, null flat. That basically means the 3 supplier transaction times are equal. Right? Now you might say that, you might get a question that, hey, what if they are not equal? Right? So if you get these kind of cases where the p-value here is less than 0.05, that means at least 1 sample is not equal, then we do this post-hoc tests. The post-hoc test will basically help us identify which of that sample mean is significantly different. And in order to apply that, we do 2-key test. We call it as 2-key test. Again, do a question mark of 2-key test to understand what is that test. Find that. Compute 2-key on a significant differences test, which basically does 2-sample t-test. Internally, it is taking 2 samples as a pair and checking which is different. Let me show you. I'll get all the same results. All are equal is what we get. So it is first checking A to B. And the p-value is 0.08. Now this is greater than 0.05. P high, null flat. They are equal. C to A, greater than 0.05. C to B, this is also greater than 0.05. So 2-key test is basically doing the pairwise comparisons. If, right, you don't have the 2-key test, then you probably have to do the this test manually. Now, in the 2-key test, it would basically tell us which of the supplier, if there is a supplier whose transaction times are different, it would reveal here. Right? So that's basically how we do post-hoc tests, which tell us which supplier is different. So we'll also do a non-test, but before doing a non-test, I want to talk about a little bit more detail about Anova test case. The Anova test case is basically called as analysis of variance. Analysis of variance. Why we need variance here, right? So let us understand that. Let's say I'm taking three diet programs. You can imagine the same 3 samples that we have taken, right? In the previous case, we have seen the transaction times of 2 suppliers. Assume that the same data is here. But yeah, I'm giving different names here. I'm taking a smaller sample. Diet program data. So I have 3 diet programs, right? And the nutrition expert, right? She randomly assigns equal number of participants to each of these groups. Let's say I have 10 volunteers, 3 different 30 volunteers are there. And I'm assigning them to these diet programs. Basically, I'm saying that, hey, these 10 people, you follow Atkins. You always have to follow Atkins diet program. These 10 people have to follow South Beach diet program, and these 10 people have to follow the GM diet program. Yeah, due to the lockdown, everybody is at home, and yeah, we are developing a lot of food, homemade food, especially people who have who are basically staying with families. For them, yes, this example is more apt. You need to follow diet programs. Otherwise, yeah, you know what happens. Post the lockdown, we will not be able to identify, right? So the diet programs are being analyzed here, and the nutrition expert, when she was studying these diet programs, she collected, right, the weight losses. So for the 3 volunteers, 3 groups, let's say after a month, she collected the average weight losses. So people have lost some weight here, people have lost some weight here, people have lost some weight here. We take weight, average weights, and those average weights are given here. Now, what can she conclude about the diet programs? Yeah, if you think about the scenario, can I say this South Beach diet program, which is saying 7 kgs, is the best diet program because this is, right, affecting the weight loss program in such a way that the people are losing more weight. The diet programs are basically designed to make sure the volunteers are shedding out their weight. And 7 kgs is a big number when compared to 4.5 and 5.3. But the problem here, if I have to consider like this, the problem here would be, what if I have an outlier in the second South Beach diet program case? There might be a scenario where I have an outlier, right? So if you have such outlier, then obviously your mean gets affected. And probably because of that, I see 7 kgs weight here. Maybe one of the volunteer is very, very fat, maybe 150 kgs, 150 kilograms. So when the diet program was assigned to him, obviously he would have lost weight a lot. Maybe he lost 20 kgs weight, assume, just remember. Whereas the rest of the people in all the diet programs were losing 1 kg, 2 kilograms, right, 5 kilograms at max. Maybe, just saying. So the 20 kilograms example, right, would be an outlier, isn't it? So in such cases, performing or in such cases, taking means may not be the appropriate scenario. Right? Alright. So you might say that, hey, if we have an outlier, then definitely there might be a scenario where it is not normal data. It may be non-normal data, right? What if it is normal data and still you have an extreme weight? Think about it. Think about it. We cannot just make conclusions saying that we always go with medians if we have outliers. We go with medians when we have non-normal data. Now, if you look at the scenario, I'm trying to explain here the Anova. We are taking the 3 samples and plotting the averages. Okay, there might be 2 scenarios that we might arise. Understand the logic. Scenario 1 or scenario 2. Any one of these cases might occur. In scenario 1, if I take the 3 diet programs and measure the averages could be like this. And this 5.6 is the grand average. Grand average basically means the average of these 3. Now what is happening here is 4.5 is right at this distance to the grand average. 5.3 is at this distance, closer distance to grand average, and 7 is a little higher than grand average. Okay, now if you look into this diagram, okay, can I say that this is losing, this is influencing a huge weight loss? Don't look at the names and all that, just try and concentrate the picture, concentrate at the picture. This diet program, can I easily say that is basically losing the, influencing the people to lose more weight. Whereas if you look into the scenario 2, this case might also arise. Now, the problem in this scenario 2 is that the weight losses of individuals within the diet program is a lot. Some person is losing 1 kilogram, some person is losing 2 kilograms, some person is losing 7 kilograms, some person is losing 10 kilograms, as you know, right? Similarly here, the variances in the diet programs is very, very huge. The point that I'm trying to say is, if you look at a person who is in, let's say, the second diet program, there are few people who are losing weight which is equivalent to the average of this diet program, and there are people who are losing the weight which is equivalent to the average of this diet program. So how would I conclude it? It would be very, very difficult to compare these groups because the variance within the group is very high, right? But if you look at this, the weight losses are more consistent, right? Close. The variance in this case within the group is very less, whereas the variance in this group is large. Right? We need to understand that not individual data point, not all the individual data points would remain constant. If I have to explain in the diet programs, not each person is going to respond identically to the diet program to give you identical weight losses. They will vary. Now, in this case, if I have to compare the groups, then it would become easier for us to compare when within the group variations are less. If I have more within the group variances, comparison becomes difficult. Right? So this is where we need to compare the variances. That's the reason. And hence the test that we are doing is called as analysis of variance. And we are basically looking at within group variance and between group variances as well. If I explain that, let's say I have the type programs, right? Let me draw this. So I have x1, x2, x3. Okay? And let's say I have 1, 2, 3, so forth, 10 volunteers. So the weight loss that I get, I'm recording it here. So I'm calling it as xij. So I'll say I is 1, 2, 3, where j is 10 records. So I'm saying xi, j. That means x11, x12, x13, so on and so forth, x21, so on and so forth, x31, so on and so forth. Right? This is my data. Yep. That is represented here. Xij. Only for representation purpose. Now, we consider the weight loss. Okay, we need to calculate average as well. So I'll call it as xi. X bar I, I'm plotting it here. Okay, the average weight loss for each diet program. Now, this xij is the weight loss, right? Considering the weight loss of the group, right? How much weight loss does this person has? There might be some variation, right? The group's average could be 4.3, but this person might have lost only 2 kgs. So there is a deviation. That deviation is measured as error here, EIJ. For each and every volunteer, we are measuring EIJ and marking that here, which is nothing but the difference between the weight loss to the average weight loss of that respective group. Then we measured the grand average as well. That grand average is the average of these 3 averages. X bar 1, X bar 2 and X bar 3. Grand averages. Average of these 3 would be your grand average. This is how we represent it. Okay, this one. Average of averages. And I'm saying, how is this average, the first group's average, differing from the grand average? That is marked as TI. We call it as treatment. It's just a representation. Okay. And then we can also check how is each individual volunteer's weight loss deviating from the average of averages, that is grand average. That is TOTI. So we are marking all this in this diagram, all the differences. We are marking it here. And if you see, the total weight loss that you are seeing, TOTIJ, would be equal to EIJ plus TI, isn't it? So you can say this is your equation. And I'm squaring them. When I square them, I get this result. Statistically, don't worry about the calculations. When you square them, you get this. So it's like a square plus b square plus 2ab. Because it's not squared, the differences that you are getting would always nullify and become 0. So we are left out with a square plus b square. Okay. Now this is sum of squares treatment. Sum of squares treatment means I'm taking only the differences and squaring the differences. So I say xij minus grand average whole square. That is this calculation. Treatment, this is xi bar minus x grand average whole square. And this is x minus x bar whole square. We are only talking about sum of the squared differences. But this sum of the square differences, when you are comparing, is definitely getting affected with the number of volunteers that we might have. If I have 30 volunteers, right, then this value will get influenced by the 30. If I have 300, then this value gets affected. Similarly, if 30 volunteers are there, then I'll get 30 results, 30 calculations. If I have 300, I'll get 300 calculations. So the number is getting affected with the number of volunteers. So what we do? We calculate variance. That means we are doing average. We have to do average of this deviations. And we know degrees of freedom formula. Remember the variance formula for sample is, variance, right? My bad. For the variance, the formula is summation of x minus x bar whole square divided by degrees of freedom, n minus 1. So these calculations that you are seeing will get normalized by applying that degrees of freedom here. Mean square treatment. The sum of the square treatments was summation of x I bar minus grand average. This was the sum of square treatments. That means I have 3 suppliers. So I'll do a 3 dichromes. Right? Here we call it this thing R minus degrees of freedom. We'll go back to the previous slide. This is the treatment. This is the treatment that I'm talking about, which basically is summation of x bar minus w bar whole square. 3 groups are there, right? So degrees of freedom is n minus 1. This sum of the square errors are talking about all the volunteers. 30 volunteers are there, right? So these volunteers are basically from 3 groups. 10, 10, 10. So here you have 3 n's. For each of the supplier, I say n minus 1, n minus 1, n minus 1, which becomes n minus 3, where this 3 is nothing but your sample size. So n minus r is your denominator here. Degrees of freedom would be n minus r. Now the ratio of these two is your F statistic. And in ANOVA, F statistic is used. Between group variation, I want to ultimately find out the variation between the groups. But it can affect, or the decision can be affected by within group variation. So ratio of these two is your F statistic. And this statistic gives us the p-value. Using the p-value, we conclude the hypothesis. And your hypothesis, null hypothesis says all are equal. Alternate says at least one is not equal. If you don't do okay, I think I need to look at the questions here. I get a lot of questions which are very, very basic. You need to look at what is the formula of variance. You need to understand what is the formula of variance. What happens if I don't do square? Probably you can go through the YouTube videos which talks about the basic statistics. Go through them. Try and understand how the variances are calculated. That would probably give you an understanding on why we are squaring. Whether it is equal samples or unequal samples, Adi Reddy, because we are doing normalization, right? It does not affect on the number of samples, right? Even if it is unequal samples, no problem. All right. So this is basically how we deal with ANOVA, which basically says between variance, between group variance or variation between the groups, right? That is what we need to find out, which gets affected by within group variance, right? So that's your ANOVA test case. Now let us also try and understand ANOM test case. So if you look into this slide, we have ANOM test case as well. The ANOM test case is analysis of mean. This is analysis of variance. Analysis of means basically is the test which tries to tell which of the means from the several means that we have, right, is different from the overall mean. Whereas the variance is talking about which of the means is actually different. In ANOVA, we can tell whether one of the means is different, but which is different, we will not be able to tell unless until we do post-hoc test, two-key test. Whereas in ANOM, right, it tells which means from the several means that we have here, right, is different from the overall grand mean, right? And the ANOM test basically gives us a diagram, pictorial representations. So let us try and do that. Okay, the differences, if I have to talk about ANOM and ANOVA, right? ANOM basically assumes that the data is normally distributed, but it can also be applied for Poisson distribution as well. Whereas ANOVA, we assume that the data is normally distributed. Both of them should have the data normally distributed basically. In ANOM, we are trying to see the variation around the overall mean, right? But in ANOVA, we see variation among each other also. Variation among sample A, sample B, sample C. That is ANOVA. Whether sample A is better compared to the overall mean, or sample B is better compared to the sample mean, or C is better compared to the overall mean. That is ANOM. Right? And here, which mean is better, we can identify. Whereas in ANOVA, we cannot. So in order to do the ANOM test, we need the package called ANOM. To do the question mark of ANOM, this ANOM decision charts. It gives you the visualization charts. So I'm taking a dataset water filter. The water filter data basically is consisting of the brands. There are 7 different brands of water filter manufacturers. Different brands of water filter manufacturers. And these filters are being analyzed for their capacity to control the growth of the bacteria. Comparison of water filters. Filtering performances of 7 brands of water filters. Okay, so if you say structure of water filter data, you see we have brand 7 levels. As I said, there are 7 different categories. And colonies is an integer. These are the number of colonies of bacteria which are growing. Right? So you can also do table that will also tell us the breakup. So brand 1, I have 3 different filters. Brand 2, brand 3, so on and so forth. I have these filters. Now, in order to do ANOM, first I am loading multi-computation package. And here I am doing linear model. LN. On the water filter, colonies is being analyzed with respect to the brand. Categorical data. I have greater than 2 cases. Remember here, I don't have brand 1 and brand 2. If I would have done, if I would have brand 1 and brand 2, then probably I would have either done 2 sample t-test or paid t-test. But here I have greater than 2 brands. So I'm doing ANOM. And using this model, I'm applying linear hypothesis testing, generalized linear hypothesis testing, or you can say Gaussian linear hypothesis testing as well. So I'm performing that, and this would give us the result of colonies. Okay? Some two-sided test, basically we are saying whether they are equal or not equal. We will see the diagram, and then you will be able to identify what does ANOM actually talk about. Look at this. So ANOM gives you this decision charts, and it fixes the upper limit, decision limit, and lower limit. Okay, these are your significance values, upper and maximum. And this line that you are seeing is the grand average of number of colonies that we have, grand average. Comparing to this grand average, you can see the brand 1 has less than the significant value. So probably this is the best filter that we can see. And brand 5 has more number of colonies. These are the probabilities that you are seeing here. These are all the probabilities. Right? Within the limit and outside the limit, you can see this is outside the limits and this is within the limit. Accepted. Now you basically have to do whether you have to decide whether two-sided or one-sided test needs to be applied here. And if I have to look at the diagram, then I would take brand 1 as the best filter because it is basically filtering a lot of colonies, bacteria colonies. Right? So this way, ANOM is trying to compare the averages. These are all the averages with respect to the grand average. Whereas Anova was trying to compare between the groups. The averages were compared between the groups. Here we are not comparing between the groups. We are comparing it with grand average. This is the difference in ANOM and Anova. Right? So let me take your questions now and see if you have any questions. Let me try and answer that. Okay, I see a lot of questions here. When we have 4 and what if one combination fails variance test? Yeah, we do ANOM, right? Sriram, that's what I've said. We follow the flow chart. Variance test, even if one is failing, you need to come to ANOM test. We then will be able to compare which mean is actually different. It is we should always make an assumption for external conditions, right? Given business problem, there is no way of checking it. If you understand the business problem, Maurya, you will be able to understand the external factors. And it is not one's decision to take, it's not your decision to take. You basically have to decide that with your, with the decision of, along with the management, basically. That's what my intention is. You need to basically take that call along with your management. Okay? All right. Then, why are we checking the variances? That's what I have explained, right? Maurya, did you understand? I'm assuming you have understood. I'm looking at the questions now. I'm assuming I've answered your question. We are looking into variances. Ultimately, the test name itself is analysis of variance, if you observe. And to get the F statistic, we need to look at how these variances within the group are there. Because if the variances within the group is less, then comparing between the groups would become very easy. Right. Any further questions, anyone? Okay. I see no questions. All right, friends, if no further questions, thank you so much. Hope you have enjoyed the session. Learned about. Okay, I see your questions now. Okay, my question regarding variances was during the previous conditions, not for ANOM. When we. Okay, yeah. Hey, thank you, Alicia. Thank you very much. And yeah, just to gain more knowledge, keep following our WhatsApp. Keep following our WhatsApp group for more information on such webinars, and do subscribe and follow our YouTube channel as well. And to these mind maps, you can always refer to the website. And if you have any queries, please get back to us. We would be very glad to assist you and address your questions. Until next time, thank you so much. Keep safe, stay safe, and enjoy the weekend. Thank you.